So, good morning, my dear students. Welcome back to my EMF class. Okay, today I am going to discuss about the concentration cell with the transference, and thereby we are to define the liquid junction potential, and also we are to derive the expression for the liquid junction potential. So, first of all, we have to explain what is the concentration cell with the transference and the EMF of such a cell. Okay. After that, we have to compare it with the same cell. If work without transfer, then we have another expression for each cell. Then you compare this, then thereby we can derive the expression for the liquid junction potential. So, suppose an electrolytic concentration cell, with transference. That is, it is a cell consisting of two solutions of an electrolyte having different concentration in two half cells which are in direct contact with each other and having same identical electrode dip in it, or in contact with the identical electrode, having identical electrode assembly. Again, an electrolytic concentration cell with transference can be designed by taking an electrolytic solution of two different concentration. Okay, that is a two solution of an electrolyte having two different concentration in two half cells with the same type of electrode which are in direct contact with each other, so that there is a transference of electrolytic material through the junction of the solution. That is a peculiarity. A typical example of such a concentration cell with transference is two hydrogen electrode in contact with the hydrochloric acid solution of two different concentration A1 and A2. Okay, A1 and A2, in which the HCl solution are connected directly, or the two solutions are in direct contact with each other. That can be schematically represented like this. That is, two hydrogen gas electrode in contact with the HCl solution of two different concentration which are in direct contact with each other, like that. Can be represented like this: platinum, then hydrogen gas at 1 bar or 1 atmospheric pressure, okay, which is in contact with the HCl solution of activity, okay, aqua of activity A1, and which is in direct contact with each other, There is no solvent here, direct contact, that is HCl, aqua, A2 concentration, and which is in contact with the hydrogen gas electrode at 1 bar. So this is an assembly, a typical example of assembly of a concentration cell with transference. It is an hydrogen gas electrode in contact with the HCl solution of two different concentration A1 and A2. Assume that A2 is greater than A1. Okay. And you can see what happens in this case. The H plus ion and Cl minus ion can move one from the other through the junction. The peculiarity of this system is that the hydrochloric acid is in direct contact with each other. So, under the influence of the electricity or electric current, the hydrochloric acid can move. H plus can move one towards the right, while Cl minus ion can move towards left. That is the situation, because this is the anode, this is the current. Okay. So the electrode reaction is given below. The electrode reaction. The electrode reaction. how such an assembly is. That is, reactions are one at anode. This is the anode. This is the cathode. Okay. So at anode, at the anode, you can see at the anode, you know that this hydrogen undergo oxidation. That is half H2 for convenience. Okay, for convenience you have to take half H2 gas at a 1 atmosphere, 1 bar gives H plus aqua, H plus of activity A1. A1 aqua, there is no need to write aqua. A1, okay, A1 plus electron. This is 1. This is oxidation. This is the oxidation. Then at the cathode or right hand electrode, this is LHS, this is RHS. RHE, and okay, left hand electrode, right hand electrode at the cathode, that is H plus aqua, H plus aqua A2 undergo reduction by the electron and is converted to half H2 gas of pressure 1 bar. This is the reduction. So the overall process is liquor is getting cancelled. Okay, is getting cancelled. So H plus at the concentration A2 is converted to undergo transfer to H plus at the concentration A1. So the next result or overall process is this reaction, and electrode reaction is the transfer of H plus ion from activity A2 to activity A1. So that is the situation here. That is equation number 3. This is the overall reaction of the oxidation reduction process. In addition to this process, okay, there are certain other processes taking place across the junction or at the junction. This is the junction in which HCl of two different concentrations, A1 and A2, are in contact. They are of different concentration. Since they are of different concentration, there is a diffusion of the ion takes place under the influence of the current. Okay, there is a diffusion. Okay, there is a chance for the diffusion of the ion under the influence of the current takes place, that we are going to discuss here. So in addition to this process, there are various other processes takes place at the junction. There are various other processes taking place, occurring place at the junction, the liquid junction that I am going to discuss. You know that, first of all, look in the equation number 1 or reaction number 1. As a result of the reaction number 1, that is oxidation, that is at the left hand electrode, the concentration of H plus ion increases due to the liberation of H plus ion or due to the generation of H plus ion. So at the left hand electrode, the concentration of H plus ion increases due to the generation of the H plus ion due to the oxidation or reaction number 1. On the other hand, at the right hand electrode, RHE, the right hand electrode here, the H plus ion get consumed. The H plus ion get consumed due to the reduction process, reaction number 2. So at the reaction number 2 is reduction. At the right hand electrode, the H plus ion get consumed so that the concentration of H plus ion diminishes at the RHS right hand electrode. That means the chloride ion concentration is greater on the right hand electrode. That's the net result. So when the process takes place, okay, when the process, reaction of 1 and 2 takes place, after some time, a stage is attained at which the left-hand electrode, the concentration of H plus is higher due to its generation, while the concentration of Cl minus is greater on the right-hand side due to the consumption of H plus ion. The concentration of chloride ion is greater due to the consumption of H plus ion. Therefore, what happened is that H plus ion, okay, since the solution are in direct contact with each other, the ions are free to move from one solution to the other. When we pass current or with a flow of current, the H plus ion move from left to right. The H plus ion move from left to right, okay. Under the influence of the electric current, the H plus ion move from its higher concentration, lower concentration from left to right, while the Cl minus ion move from right to left, from its higher concentration to lower concentration. That is the situation. It's very important. So, under the influence of the current, okay, or the flow of the current, H plus ion move from left to right, while the Cl minus ion move from right to left across the junction, okay, under the influence of the electric current because of the concentration gradient. Okay, that is the situation that I explained. Then we have to pass on. We have to calculate the number of gram equivalent of H plus ion and Cl minus ion that is undergoing migration or transport or diffusion. Okay, so that we are going to do. This is equation number 3. Let be there. That is, let the transport number of Cl minus, let the transport number of Cl minus ion is T minus. Okay, Cl minus. Let the transport number of chloride ion is T minus. Therefore, the transport number of H plus is T plus. Okay, H plus, and let it be that is equal to 1 minus T minus of Cl minus. That is situation. That is the situation. Okay. Therefore, for each 1 Faraday of electricity, passing through the solution cell, T minus gram equivalent of chloride ion is transported from the right to left. Okay, for the passage of the current, or that is for passage of each 1 Faraday of electric current, or you simply say by the passage of electric current under the influence of the electric current, T1 minus gram equivalent of T minus 1 gram equivalent of chloride ion is transported from right to left. Okay, that is we are going to like this. Right to left means T. Okay, I am writing this T minus. Okay, Cl minus ion of concentration A2 is transported to left side, that is here, T minus. That is the situation. So, under the passage of the electric current, for the passage of each 1 Faraday of electric current, T minus gram equivalent of chloride ion of activity A2 is transported from right to the activity A1, like this, T1. Okay, that is right to left. Right to left. Transportation, this is the transport. So that is a diffusion. Okay, ion transport, okay, you simply ion transport. It means that 1 minus T minus H plus ion is transported from the concentration A1 to A2, from a left to right, from A1 to, okay, 1 minus T minus of H plus ion of concentration onto AT, that is from left to right. This is the situation. So that is the transport. That is the transport under the influence of the electric current, or by the passage of 1 Faraday each of electric current. T minus Cl minus ion is transported from right to left, from A2 to A1. Similarly, 1 minus T minus H plus ion is transported from activity A1, from left to the activity A2 right, like this. Okay. Therefore, that is equation number 4. This is 5. Okay. Therefore, the net transfer of the material. So, I have to calculate the net transfer of the material under the influence of the electric current can be obtained by adding these three equations, equation 3, equation 4 and equation 5. Therefore, you have to calculate the net transport. The net transport. Okay, I hope that you are following me. The net transport of the material or ion, okay, materials, that means ions or the electrolytes, is obtained by adding equation 3, 4 and 5. Is obtained by adding equation 3 plus 4 plus 5. So adding this is equation number, this first equation. So add this equation. So left side and right side you add. Okay. So the left side H plus is equation number 1. So equation 3, that is H plus of activity A2 plus T minus Cl minus of activity A2 plus 1 minus T minus of H plus of activity A1. Okay, that left side added gives the right side here, first equation 3, that is H plus of activity A1, that is equation number 3, plus this T minus Cl minus of activity A1 plus 1 minus T minus of H plus of activity A2. Then I am going to expand this equation. So, carefully listen, we look, go through the step, that is H plus A2 plus T minus Cl minus A2 plus H plus A1 minus H minus, okay, T H plus A1 is equation. Okay, and expanding we got like that. That gives writing this equation, that is H plus A1 plus T minus Cl minus of A1 plus H plus A2 minus T minus H plus A2. Next is, you cancel the common term on both sides of the equation and then rearrange. You can cancel the common term on both sides and then rearrange. Common term H1, H1A, this is. Okay, you can cancel this H1A on common side. Then H plus A2, H plus A2, H plus A2. H plus A2. Okay. So you can cancelling the common term on both sides, That is h plus a2, h plus a2, then h plus a1, h plus a1. Then rearranging. You take this term here. H plus a1. Okay, this look into this equation. This is our equation. You don't get confused. This is the equation. So taking the term, that is, okay, a2, TCl minus, okay, HCl. Oh, you take this equation, that is, T minus, you can T minus H plus A2. You take this equation from this side. From here to left side, T minus H plus A2 plus T minus Cl minus A2 gives, you take this side, that is T minus H plus, okay, T minus, okay, this side, good, right? T minus H plus A1 plus T minus Cl minus A1. Okay, that is the equation. So finally we get like this. That is T minus H plus A2 plus T minus Cl minus A2 gives T minus H plus A1 plus T minus Cl minus A1. That means T minus HCl A2 gives T minus HCl A1. So that means under the influence of the electric current, so under the influence of the electric current, for each Faraday of electric current results in the transport of T1 gram equivalent of HCl from activity A2 to the activity A1. Okay, that is the net result. The net result of this current passage is such that that is under the influence of each Faraday of electricity, T minus 1 gram equivalent of, okay, T minus 1 gram or T1 minus 1 gram equivalent of HCl is transported from A2 to the activity A1 like this. Okay, this is the net reaction. 6. Please go through this equation carefully. So we got as the net result is the transference of HCl of activity A2, T1 gram equivalent of HCl activity A2 to the activity A1. So that is net reaction. Therefore the EM of the cell, when we are applying the Nernst equation, by Nernst equation, the EMF of the cell, that is E cell. E cell is equal to E0 cell, always 0, right, in gas electrode E0 cell, minus 2.303 RT by F, N is equal to 1 F log concentration of product divided by concentration of reactant, that is A1 HCl concentration of HCl of concentration A1 raised to T1. Okay, HCl of activity A1 raised to T1, T minus 1 divided by HCl of activity A2 raised to H minus T1. Okay, that is equal to, that can be written as, that is 0, E0 cell is 0, E0 cell is 0 of hydrogen, gas level is 0, so that is minus 2.303 RT by F log A1 by A2, you replace HCl, you can remove HCl, okay, you can omit, okay, you neglect or you can omit the term HCl. HCl is concentration A1 and it is A2, therefore you can write A1 by A2 raised to T minus 1. T minus 1, or that is equal to plus, become plus 2.303 RT by F T minus, okay, log A1 by A2. Okay, that is equal to A2 by A2 by A1. So we got the equation. The EM of the such a cell is E cell. EM of such a cell E cell is equal to 2 point. Okay, you can take this T minus, that's transport number value, T minus 2.303 RT by F log A2 by A1. A2 by A1 for HCl. Since both ions are undergoing transport, okay, for HCl, its activity A is equal to, you know that activity is equal to AH plus into ACl minus, that is A plus into A minus, that is equal to A plus or minus the whole square. So the activity of binary electrolyte, the case of one HCl like a binary 1:1 electrolyte, 1:1 electrolyte HCl, both ions get ionizes in the solution, therefore activity is equal to A plus or minus the whole square. So you can replace this, therefore A2 is A plus or minus 1 2 the whole square and A1 is A plus or minus 1 the whole square. So we have the equation E cell is T minus into T minus into 2 point. Okay, I generally T minus RT by F. RT by F. Ln the equation. Log RT by F log. Okay. Okay, I'm RT by F log A plus or minus the whole square. Okay, 2 the whole square divided by A plus or minus 1 the whole square. Okay, that is equal to, this can be commonly taken as 2 T minus into 2 point, okay, RT by F ln A plus or minus 2 divided by A plus or minus 1 the whole square, that is equal to 2 T minus into RT by F ln A plus or minus 2 divided by A plus or minus 1. That's the equation. So, an electrolyte cell with a transference in which the electrode is reversible with respect to the cation H plus ion. The electrode is reversible with respect to the cation, in this case H plus ion. Then E cell is equal to 2 into transport number of anion into RT by F ln A plus or minus 2 divided by A plus or minus 1. And the cell works spontaneously with an EMF, with a positive EMF, if A2, A plus or minus 2 is greater than, or A2 is greater than, if A2 is greater than A1, it has a positive EMF and it works spontaneously. That's the situation. So remember this equation for an electrolyte cell with a transference in which the electrode is reversible with respect to H plus ion or cation. The E cell is 2T minus into RT by F ln A plus or minus 2 divided by A plus or minus 1. On the other hand, if it is reversible with respect to anion, if it is reversible with respect to anion, like a silver chloride electrode, silver chloride electrode, if it is reversible with respect to anion, the equation has become 2T plus into RT by F ln A plus or 1 divided by A plus 1 minus 1, 2. This equation. So we have two expressions. This is the E cell for an electrolyte cell with a transference in which the electrode is reversible with respect to H plus ion or cation. This is the E cell for an electrolyte cell with a transference in which the electrode is reversible with respect to the anion. Okay, like Ag, AgCl, HCl like or KCl like that. This is the HCl like this is the situation. So in that case, this is reversible with respect to anion. This cation 2T, the transport number of anion comes. If the cell is reversible with respect to the anion, the transport number of the cation comes in the expression. That you will always be careful. Okay. The next, we have to pass on to the liquid junction potential. Liquid junction potential. What is a liquid junction potential? That is E liquid junction. That is when an electrolytic concentrated cell with a transference works for some time, but for a few times, for few times, because of the transference of the ion takes place across the junction, or because the transport of the material through the junction, okay, because of the transference of the ion through the junction takes place, okay, after some time, there develops an electrical double layer. There is an electrical double layer across the junction due to the differential migrate transporting mobility, differential rate to the migration of the ion. Okay, due to the differential rate to the migration of the ion, due to the differential rate to the migration of the ion, or due to the difference in the speed of the ion, that develops an electrical double layer at the junction, across the junction of an electrolyte cell with the transference, which lead to the development of a potential at the junction, and that is called the liquid junction potential. So liquid junction potential is defined as that potential that develops across the junction of an electrolyte cell with the transference due to the development of an electrical double layer across the junction, which arises from the differential of migration, differential rate of migration of the ion through the solution. Okay, that is, if the speed of the cation and the speed of the anion are different, in that case, the cation and the anion differ in their transport number, and hence the rate of migration of the ion get different, so that there is an electrical double layer across the junction, and therefore that electrical double layer leads to the development of a potential. Okay, that has its own contribution towards the total potential of the EMF of the cell. Actually, it negatively affects the total EMF of the cell, so that it is a negative effect. So it has its own contribution towards the total EMF of the cell in a negative manner. Therefore, we have to eliminate the liquid junction potential by designing a cell. Okay. We are always careful about the elimination of a liquid junction, because it will negatively affect, it will in effect reduce the output of a battery or a galvanic cell. So once again, if an electrolyte cell with a transference work for a fixed time, that develops a potential across the junction of the two solutions because of the development of an electrical double layer arising from the differential rate to migration of the ions. Okay. And the differential transport number of mobility of the ion give rise to a development of the electrical double layer across the junction. That is why it has become there is a potential. And we have to think about how it happens. Suppose we have a junction. Consisting of HCl of different concentration, HCl of concentration lower and higher concentration. Suppose consider 2 HCl solution in which A1 is of higher concentration than HCl of concentration HCl of A2. Okay, like that. As a result of the migration of the current, you know that both HCl, H and Cl minus ion tend to move towards the right, higher concentration, the lower concentration, always. The mobility, diffusion is from higher concentration to the lower concentration. That all of you know that. Lower concentration. So when you pass a current under the influence of the diffusion, due to the concentration gradient, the H plus ion and Cl minus ion both tend to move from left to right, from higher concentration, lower concentration. But as you know that, the mobility, the ion speed, U of H plus ion, okay, U plus H plus ion is much greater than U of Cl minus ion. Therefore, T of H plus is much greater than T minus of Cl minus ion. Okay, this is a situation. Since the ideal mobility of H plus ion is much greater than Cl minus, therefore the transport number, okay, the rate of migration of H plus ion is much greater than the rate of migration of Cl minus ion. So that what happens, you know that. So after some time, by the passage of the current, the concentration of H plus ion get accumulated on the right side, or the right side, the solution become more concentrated with respect to H plus ion. While at the same time, you know that what happens here, the Cl minus ion is going only very slowly. Okay, the Cl minus ion is going only very slowly from this direction, so that this side become accumulated with respect to the negative ion. Okay, so after the passage of the current, what happened is that here in this case the dilute solution is enriched or become greater with respect to high moving, with respect to the high mobility ion, that is ion with high mobility, ion of high mobility. This is a situation you have to remember. Okay, when two solutions of such a different quantity, when HCl solution of two different concentrations separated from one another, because of the migration or diffusion of the ion, you know that the dilute solution become with a higher concentration with respect to the high mobile ion, with high speed ion or high mobile ion, high speed ion or ion with high mobility. So that in this case it become accumulated with the more H plus ion, there is a positive charge here. While this ion, this side, the concentrated solution means at the same time is accumulated with respect to the slow moving ion that has become concentrated with the negative chloride ion. So there is a development of positive double layer. This is a positive charge there. Okay, negative. Cl minus ion, Cl minus ion, Cl minus here. They are all H plus. Okay. So there arise an electrical double layer across the junction of the solution due to the difference in the speed of the ion. And this gives rise to a potential that is called the liquid junction potential. Okay. So the condition for the liquid junction potential is that if the ions are of different mobility or different transport number or different speed, the electrical double layer arises across the junction that lead to a development of the liquid junction potential. The dilute solution become more concentrated with respect to the high mobile ion, with respect to the ion with the high mobility or transport number, while the concentrated solution become more concentrated with respect to the less mobile ion. That due to the development of an electrical double layer, and that develops an liquid junction potential. And the liquid junction potential, okay, can be given by the equation E liquid junction potential. E liquid junction is equal to, that is E cell with the transfer, consider cell with the transfer, E cell, consider E cell, consider cell with the transfer minus EMF of the considered cell. The E liquid junction potential can be obtained by the difference between the EMF of a considered cell with the transference and the EMF of that cell without transference. That cell without a transfer. Okay. So that E liquid junction potential can be obtained by taking the difference between, that is the E cell, okay, that is the difference between the EMF of the cell with the transfer and the EMF of the same cell without transfer, that is E cell with the transfer minus E cell without transfer for the same cell. So we have the equation that is equal to E cell with the transfer is, E cell with the transfer is, E cell with the transfer is, you have the equation 2T minus into RT by F ln A plus or minus 2 divided by A plus or minus 1 for that coincident cell in which the electrode is reversible with respect to H plus ion cation. For the same cell, the E cell without transfer is, for the same cell if we design in such a manner that is work without transfer is RT by F ln A plus or minus 2 divided by A plus or minus 1. So that is the situation. That is, remember how this equation comes. Without transfer, the equation is, you have to remember, with the transfer is E cell with the transfer is T minus into RT by T minus into RT by F ln A plus or minus the whole square 2, the whole square divided by A plus or minus 1, the whole square. That is the equation. Okay, and this 2 comes here. So we have the equation 2 T minus into RT by F ln A plus or minus 2 divided by A plus or minus 1. But the same cell when work in the without transport, the equation is E cell is equal to RT by T minus term is not there, RT by F divided by F ln A plus or minus, okay, it's not square because only any one of the ion is undergoing transport here that you are seeing, either A plus or either, that is in this case A is equal to A plus or A minus. Okay, therefore A2 is A, okay, this equation A is A plus or A minus, A plus or A minus, therefore A is equal to A plus or minus. But in this case, with the transfer you have to know A is equal to A plus into A minus, therefore is equal to A plus or minus the whole square. Here it is O, A plus or A minus. The case of a cell without transference, A is A plus or minus or A minus, or A is A plus or minus. The case of cell with the transfer, A is A plus into A minus or A plus or minus all square. That is the situation. So in this case, it is RT ln A plus or minus, either positive or negative, divided by A plus or minus 1. This is the equation. So we have the equation. This is the equation. Okay. So now the situation now becomes, that is equal to RT by F ln A plus or minus 2 divided by A plus or minus 1 into 2 T minus, okay, minus 1. This equation. So as the expression for liquid junction potential. The expression for the liquid junction potential is given by for the electrolyte cell with transference in which the electrode is reversible with respect to the H plus ion negative cation is, that is 2 into transport number of anion minus 1 into RT by F ln A plus or minus 2 divided by A plus or minus 1. On the other hand, if the cell is reversible with respect to anion, then E liquid junction is the second case. Electric potential is RT by F ln A plus or minus 1 divided by A plus or minus 2 into 2 plus minus 1. This equation. Okay, this equation. Then, you know that replacing this, but you have to remember T plus T minus is 1. When you replace this equation, like this, that is equal to RT by F ln A plus or minus 2 divided by A plus or minus 1 into 2T is equal to T plus, okay, 2T plus minus, that is, you can put it this 1, okay, minus 1 is minus T plus T minus, okay, you can put it as minus T plus minus T minus. So this now the equation now become, that is equal to RT by F ln A plus or minus 2 divided by A plus or minus 1 into 2T plus minus 2T T plus, that's T plus minus T minus. So, liquid junction potential of a electrolyte cell with the transference in which the electrode is reversible with respect to cation is the difference between the transport number of the cation minus transport number of anion into this term. Okay, that's the issue. On the other case, it becomes T minus T plus. That's the difference. Anyway, so if the liquid junction potential depends on the difference with the transport number of the cation and the anion. If T plus is equal to T minus, so that U plus is equal to U minus, then that term becomes 0. So liquid junction potential eliminates. So if an electrolyte in which the cation and anion have the same ionic mobility, so the transport number is the same, then T plus and T minus cancel each other, so that they become 0, so that liquid junction potential becomes 0. That is why the principle of the salt bridge. The salt bridge contain the electrolyte of both the inert electrolyte KNO3, ammonium nitrate, etc., in which the cation and anion have the same ionic mobility. You know that is the salt bridge contains certain inert electrolyte. So the salt bridge, we are taking certain inert electrolyte not to avoid the liquid junction, because the inert electrolyte like KNO3 or KNO3 or ammonium nitrate, etc., they have KCl, etc., they have the cation and anion have the same ionic mobility. They have the same ionic mobility, so that there is no difference between the cation and anion ionic mobility. Hence, there is no transport difference in the transport number, so that the liquid junction potential can be eliminated. So, examination, you can ask the question, why? How the liquid junction potential can be eliminated by introducing salt bridge. By salt bridge, we can introduce, that is, direct contact with the electrolyte can be prevented. And another is, we are using the salt bridge certain inert electrolyte in which the cation and anion have the same ionic mobility, therefore they have the same transport number, thus it can eliminate the liquid junction potential. Okay, thank you very much. Suppose we are using an electrolyte in which the electrode is reversible with respect to cation. The electrode is reversible with respect to cation. This is a cation, RT by F ln 2t minus, okay, we have that sum. 2t minus. Cash is wrong. Please go through this. Some mistakes there. 2t minus okay, minus t plus minus t minus. So we have the equation. We have the 2t minus t minus, that is t minus. T minus t plus. So sorry for the mistake. So for the electrolyte in which the concentration in which the electrode is reversible with respect to cation, then the transport number, the liquid junction potential is directly proportional to transport number of the anion minus transport number of the cation into this term. On the other hand, if it is reversible with respect to anion, EAL is like this: T plus minus T minus. Okay. That then it depends on the difference between the transport number of the cation and anion, T plus minus T minus into RT by F. Ln A plus or minus 1 divided by A plus or minus 2. That is the situation. But this is EL. We have two equations. One is like this, EL is like this. Okay. And other is EL is like this. This is for the reverse electrolyte in which the electrode is reversible with respect to anion. And you have to transfer number the cation minus transfer number. This is the reversible cell, that is electrolyte cell in which the electrode is reversible with respect to anion. Cation is transfer number anion minus transfer number of cation. That is ideal gas electrode with HCl. This is the silver chloride electrode with HCl. This is the situation. Okay, you please go through this equation carefully for derivation. What I wish to say is that if there is a difference between the transport number of the anion and the cation, then if the solution is direct contact, there is a liquid junction potential. So in order to avoid the liquid junction potential, you can do mainly a constant cell. You have to use that is okay. Then in that case you can eliminate generally. Avoid direct contact solution, and second is use a salt beach in which containing electrolyte of cation and anion having the same ionic mobility or train transport number like KNO3, ammonium nitrate, KC acid. Okay, thank you very much. Hope that you have followed my equation. So liquid junction potential is the potential that leveled up at the junction of a two electrolytic solution having the same concentration of electrolyte having the same concentration due to the development of the electric double layer across the junction arising from the differential rate of migration of the cation and the anion. In that case, the dilute solution become more concentrated, the dilute solution develop that charge of the ion which have high speed, while the concentrated solution develops that charge of the ion which have low mobility. That's the thing. So when we in that case, the dilute solution develops that charge of the ion with a high mobility, while the concentrated solution develops that charge of the ion with a low mobility. That's the best thing. So in this case, H plus ion become more concentrated, therefore that the dilute solution develops positive charge, while the Cl minus ion is less mobility, have low mobility, therefore the concentrated solution become negative charge due to the accumulation of Cl minus. Typing up, I am winding with the class. Okay.